So in this video, we'll be looking at spans again. Um, Mostly what I wanted to say was span of a vector space is important because of something. Oh wait. So I think first of all, before I tell you why it's important, in fact, it's important because it's important because it is the smallest subspace we can have. So the span of U and V is the smallest subspace of V containing U and V. So first of all, I think we need to define what a subspace is. But it's actually pretty simple. So if V is a vector space, in fact, why am I writing it out? Okay, if V is a vector space, then let's say over F, then and U is a subset of V, then we say U is a subspace of V if U is a subspace if it's a vector space, if it's also a vector space over F, right? Okay, so basically, if V is a vector space and U is a subset and also a vector space, then it's a subspace, okay? So first of all, we want to see that the span is a subspace. So, I mean, let's say U, so these are vectors. Let's say U and V are elements of V. And let's say that U now is the span of these vectors U and V. Okay, so in the previous video we showed that U is indeed a subset of V. So this is capital V we're talking about. Capital U we're talking about as a subset. Now we want to show it's also a vector space over the same field. But that's kind of obvious because, okay, so if something's in, so let's say X is X and Y are in U, then we know that everything in the span is just a linear combination of U and V. So that means there is A1 U plus A2. Oh, so these A's are just numbers. Let me just, so I'm going to put yellow as numbers because that's how I usually do it. A1, alpha 1, alpha 2, and V, and this is equal to X. And we can do betas for So beta 1, beta 2, and u v for y. And so we want to show that that the sum x plus y is in u, and x times some number is also in u. So x plus y would just be alpha 1 plus beta 1. Okay, and again, I keep forgetting. Should be yellow. No. Oh, why am I writing it all tilted? Anyway, alpha 1, beta 1, u plus alpha 2, beta 2, v. And clearly, this is in, what do you call it? This is in u, because we said every combination is in u, because it's a span. And so we have that x plus y is in u. So that's what is part. So to be a vector space, we need x plus y to be in u, and some field element times x to be in u. So we're halfway there. So let's just write that down. X plus y is in span. Oh. Okay. And now we just want x times something to be in the span of u and v, and then we're done. We've shown that the span of u and v is a vector space. So let's go ahead. Let's multiply x by, so we did alpha and beta. Let's do gamma then. Gamma times x is equal to gamma times alpha 1 u plus gamma times, so x was alpha 2v and if we just put brackets around it now, let's see, like that, we just see once again that this is just a linear combination of u and v, and so this is in u. And so let's just be specific here. Gamma is in the field. And so let's just wait. I just want to move this. Gamma times x. Whoa. X is in the span. span of U V. And so the span of U V is a it is a vector space over the field F. So I hope in this video that you've understood what we mean by a subspace, and that the span is a subspace. The span also turns out to be the smallest subspace, right? So you know that a subspace should contain, the smallest subspace containing U and V. Any subspace containing U and V should have every combination of it, and so if a subspace contains U and V, then that contains the span of U and V. So what I mean is, if I think you've kind of understood, and I think just writing it down will just make it more complicated. So that's it for this video, and thanks for watching.